Good afternoon. My name is Jayant Mandi. I'm from Prime University, Brazil, and today I'm going to present my paper, Differentiable Optimisation Layer with an Interior Point Approach. This work is done under the supervision of Professor Thias Kunz. So first I'm going to introduce our problem setup with a motivating example. Then I'm going to lay out our methodology. In the result section, I'm going to compare with the state of the art before finishing my talk with concluding remarks. So, investment in stock market would be a good example of the kind of work we are focusing on. Stock market investment should abide by some set of rules, or technically speaking constraints, with the objective of maximizing future profit. So a CP solver can solve this problem and tell us how to allocate funds to maximize the profit if the future stock prices are fed to the CP solver. But as the future prices are not known, so the best we can do is to use a machine learning model to predict the future stock prices and then feed these future predicted stock prices to the CP solver. So to emphasize, here the purpose of the machine learning model is not to generate accurate predictions, but to generate predictions which will enable the CP solver to maximize future profit. So these are the example of predict plus optimize class of problem where machine learning and combinatorial optimization join hand. Here the final objective is to solve a combinatorial optimization problem, but some of the coefficients of the combinatorial optimization problem are not known, so machine learning model is called to predict those coefficients. So in this work we will train a machine learning model end-to-end for predict plus optimize LP problem, and we will do this using a novel differentiable LP solver by which differentiates the homogeneous self-dual formulation of the LP. So in general we are focusing on combinatorial optimization problem, but for this work will be limited to LP or integer LP or mixed integer LP. We will also assume that the C parameter which appears on the objective function of the LP are not known, so that must be predicted using the machine learning model, whereas the A and B are known to us. So what is an end-to-end training? In end-to-end training of predict plus optimize problem, the objective is to train a machine learning model to minimize regret. Now what is regret? Regret is the loss for using the predicted coefficient instead of the actual coefficients which are not known. Now as in standard machine learning model is trained where it updates its model parameters by differentiating the loss function which it aims to minimize with respect to the model parameters. Now as in this case we are trying to minimize regret, so we have to differentiate regret with respect to the model parameters, and using the chain rule of differentiation this can be decomposed in three portions. Now the first and the third portion are quite easy to compute in this case. The key challenge lies in computing the second component, where we have to find the derivative of the solution of the CP solver with respect to the predicted coefficients which is fed to the CP solver. So that means we have to perform an arc-bin differentiation, and this is the key challenge we are facing. So how we do this? So first we will assume a continuous relaxation of the integer problem, and that means we are approximating the feasible region, discrete feasible region, by a convexal approximation. Now previous work by Wilder et al. Has shown that such continuous relaxation always exists for any problem, and moreover their work also shows that such approach are sufficient for most LPs, and this produce a satisfactory result. So basically our problem has become a LP problem, that means a convex optimization problem. That means the KKT conditions are necessary and sufficient condition for optimality. So the X is now related to C at the optimal point by the KKT conditions. So ideally we can differentiate the KKT conditions and find the derivative of X with respect to C. But for that, as equation 3 shows, that fxx, which is the double derivative of objective function with respect to x, must not be 0. But for the LP problem we are focusing on fx is 0, so we run into a problem. So what we do, first we will study how an LP problem is solved in practice. And homogeneous self-dual embedding is an interior point method which is the most efficient for solving LP, and this is the state of the art, and this forms a extended optimization problem from the actual LP, which is also a self-dual. Now the advantage of this approach that it can start from any point, even if it is infeasible to the actual optimal point, optimization problem, and it can always find a solutions which is strictly complementary. That means some of the variable will be 0 at the optimal point, and from this property it can find out whether the actual LP problem is feasible or not. So it can certify infeasible problem. Moreover, as it is self-dual problem, the primal, if both the primal and dual problem of the actual problem is feasible, then the central path the algorithm follows will lie in the feasible region of the primal and dual problem. So the duality gap will be a good measure of how far we are from the optimization actual optimal point. So in a sense, this homogeneous self-dual embedding has more number of parameters, and it contains rich information about the optimal point and the solution process. So this motivates us to differentiate the homogeneous self-dual embedding. But as I mentioned, it has some strictly complementary conditions, so that the optimal point some of the variable will definitely be 0, and then again we run into a same problem. So to overcome this, we propose that we will not solve till the optimal point, but we will stop before the optimal point when some of the variable will goes below a threshold. It comes with another advantage, which is, as we are not solving all the iteration till the optimal point, we save some of the iteration. As a result of that, in the forward pass will be less time consuming, so the training time will be less. Just to emphasize, the same thing can be done with the KKT conditions too. We can stop before the optimal point and then differentiate the KKT conditions too, and we did it, and then compare with the approach of differentiating the homogeneous self-dual embedding, and our result shows that the differentiating homogeneous self-dual embedding produces fewer lower regret. So that means this is more effective. Then we compare our approach with the two-stage approach, with SPO, which is subgradient based approach, and QPTL, which also differentiate the KKT conditions, but first it adds a quadratic term which is not part of the actual LP, and we show that we are able to outperform both two-stage and QPTL and marginally outperform SPO. So to conclude, we propose a differentiable optimization layer for linear program based on interior point method, where we differentiate the homogeneous self-dual embedding, and we show that differentiating homogeneous self-dual embedding is more efficient than differentiating the KKT conditions. And with this framework, we implemented end-to-end training of integer LP without the need of adding a quadratic term, and our experiment shows that we are able to outperform the state of the art. Thank you.